So I'd like to kick this off, and for the folks in the room, I can see you via video. I'm just curious, how many of you are APA members and also read planning? And then what I've got up here is the March issue. It was about smart cities, and I want to kick this off because a lot of the groundwork that you're going to do in preparing your communities is all revolving around what everybody's calling smart cities and a lot of the technology that's out there. And the backbone of that is what Mike and David are going to really talk about. Beyond that, though, it's really important to understand that your data is your infrastructure moving forward. And if you don't currently have an open data policy, it's something that you should be researching and helping implement in your jurisdiction or helping your clients implement. And an example, too, of something that the city of San Jose is doing is they're taking an initiative to actually create an HD map that they will own and be able to distribute to technologists as they come to the city to do different work, whether it's autonomous vehicles or remote sensing and data collection. So we're going to move on to the June issue of planning, and hopefully you guys have been reading these as they come out for you, because these are very contemporary and very well written. But the thing I want to highlight here is about curbs and curb control, and one of the focuses of this issue is Chord's Surveyor mobile app and how that applies to data collection and data collection methodologies, and making it much easier to actually get out in the field and evaluate the resources and assets that you have available. David's going to kind of dive in on some of his slide decks to show you some other alternative data collection methodologies and applications that are out there. If you aren't already aware of and have taken a look at, but a great way of applying the data is through curbside management and practitioner's guide that the ITE developed in conjunction with Fair and Peers. So a little bit of history, just a remote sensing geek, and Landsat is, a timeless collection of imagery of the Earth and Earth observation, and has really laid a lot of groundwork for computer vision science over the last 47 years. So it's an amazing resource. If you don't know much about it, I encourage you to check it out. It also opens the door to a variety of other remote sensing and satellite imagery, which can provide a huge advantage to a variety of resource development and planning-based work. So I encourage you guys to educate yourselves on those resources that are available. So Hype City is something that came out of the 80s, but it really is the idea of preparing yourself for certain tech firms coming to you and representing solutions to problems that you do and don't have. And sometimes, a Facebook's going to come to you and ask, hey, we've got a great new corridor-based Wi-Fi network that we want to deploy in your city to help your patrons and constituents have better access. But the problem is that they're going to have some jurisdictional debt, and they're not going to understand how to get a permit to put equipment up on a traffic signal in order to have this great Wi-Fi network proliferate through the city. Another big problem is being able to have your jurisdictional staff or your public staff or the consultant staff understand what some of these tech firms are actually advocating and working on, and being in that space and sharing the same kind of language and technology space that they're working within. So just changing topic real quick to kind of lay it a little bit more of a primer for what Mike's going to get into, is getting into the difference of raster and vector imagery, and or raster imagery and vector data. And a lot of it is, I'm sure most of you people there have been using aerial imagery and are familiar with street level imagery. But, you know, a bigger question is how many of these still digitize your own data? You know, that's something that 5 years ago, 10 years ago was more commonplace than what it is today. And I believe today you have more data being produced from raster than vectorized data being produced. So without further ado, I'll let Mike Flaxman jump in here. And
thank you. So this image is a little nod to Ornstein's ladder of public participation for you planners there. So we've got robots on ladders now, and we, as planners, have a set of issues to deal with. Next slide, please. So I wanted to talk about basically what is machine learning as it currently really exists, not in the sci-fi movies. So what can it do, and what pitfalls do we need to be aware of? Next, please. So deep neural nets are a fundamentally new approach to computing, and that part isn't hype. It really is quite different than what came before it. The neural part is a little bit hype, I would say. These are inspired by human brains, but I like to say they're not as smart as your average hamster. But your average hamster is smarter than some people realize. And so they're quite good at some things. We'll show you what they're good at in a minute. But they're neurally inspired, and yet they have some real limitations. And so that's kind of what I'd like to go over. But the basic premise is that they're built in layers, and a typical real world example, unlike this diagram that has 3 layers in the middle, has something like 100. And those layers are trained using a large set of data, but they're not programmed. And so it really is quite different than conventional programming. I spent a lot of time dealing with conventional programming, and you have to write a rule for everything, and you have to think of every edge case. You spend most of your time trying to codify rules. And what is different about these systems is that they learn only by example. And so along the bottom, you see an image of a woman's face as seen by the neural net. And so you can take imagery into these deeper neural nets, and it gets hierarchically decomposed, and it works from the bottom up. So from the pixel level up, it finds edges and things that are kind of low-level primitives. Then it finds texture patterns kind of in the middle layers. And then as you get to the higher order layers, you see things like faces or eyes and higher order concepts, essentially. And so it's still quite difficult to figure out exactly what these are doing. That's one of the issues. But when you peer into them a little bit, you get that overall organization consistently coming through. Next slide, please. So the other thing to be aware of and cognizant of is these things live and breathe very large training data. And so that's where they're not as smart as a hamster. You could teach a hamster the difference between, you know, a trap and a piece of cheese, probably with 10 training cycles. But machine learning requires thousands and thousands of training cycles. It's not quite so bright. But given a very large amount of data, they can do well. And so the limitation in the real world today of using these systems has more to do with the training data available than almost any other single factor. So what is possible to do with these systems often revolves around what you have data for. And I think the good news for planners is that GIS data can sometimes be used, and we have a lot of that. We don't have a lot of perspective imagery that's labeled. And so this crazy example here shows you, kind of what's needed even to do actually one of the simpler levels of machine learning, which we'll talk about in a second. But a simple level is to put a box around things and identify it. But of course, in perspective imagery, you've got the motorcyclist in front of the minibus, in front of half of the person or the truck. So you have occlusion, you have shadows, you have noise. All of those things that would be hard if I asked you to do this task by hand are actually hard in terms of generating training label data. And David's going to show a very clever way around that he's working on. But in general, that's a current limiting factor, particularly for things you can only see in perspective view. For things that you already have several thousand examples in your GIS, you're probably in good shape. Next slide, please. So this slide kind of quantifies that a little bit. So basically on the y-axis, you've got training accuracy, and that's just in percentage, so 60 to 90%. And if you look just at the overall shape of both of those curves, you see that there's this huge inflection right around 4,000 training samples. So this is a particular neural net and its particular performance on a particular set of images. The answer isn't always the number 4,000, but it's often a number somewhere in that magnitude. And there are a few tricks you can use. There's one called augmentation, which can be used to extend the number of training samples. For instance, you can randomly rotate pictures, and that helps a little bit, but it doesn't help as much as having yet more pictures of the thing. Next slide, please. So the field kind of got started in about 2012. So there was a fellow Canadian, Russian-born Canadian computer scientist who came up with something called AlexNet, and that was 40% better than anything anyone had ever done before. And so in one fell swoop, came up with something just radically better. And then in the 7 years or so since, the ability of these systems to recognize categories and images, as this example task includes, has gone up in accuracy from 71% to 97%. And the 97% actually exceeds human ability, at least when you start getting bored having to label 1,000 images. So, for particular tasks that are defined like this, computers are much, much more patient than humans, and can go through just reams and reams and reams of imagery. So that's really good news, I think, for planners, because digitizing is boring for everybody. So you don't need to sit there digitizing stuff the way it was previously required. But take a look at the number of images in this particular training set that was used. So 1,500,000 images. That's a lot of image data, even to classify roughly. Next, please. So I've been throwing around the term classification, but I want to be a little more precise. So there are basically 4 different types of image classification that these systems do. And these are organized kind of, depending on your point of view, from the easiest to the hardest, or from the overly simplistic to the most useful. So sometimes it's good enough to look at an image and say there's a cat there. Sometimes it's good enough to say there's a cat and it's in the center of the image. That's the localization part. Often you've got multiple objects in a scene, and especially for most planning applications, you're kind of in that realm of object detection. So you want to, for instance, count pedestrians. I'll show you in a second an example of that. That's an object detection task. You don't care that much about the details of the individual, but if it's one individual walking, that's what you want to know. And then image segmentation is the most difficult, but also the most useful general form. And so that basically traces a bounding box around every object of a type that you specify. So that can tell you how many dogs or cats are in a scene. Next, please. There's a second whole suite of capabilities from these deep neural nets, and these are known as generative models or image generation. And these have a whole set of other uses and dangers. They're most famous, I guess, getting most famous for the bottom cases, which are creating fake celebrities, or for generating user profiles that are fake and you can't tell that they're fake. But these same technologies have some good uses, which I hope to show you in a second. And the slang is called GAN, or General Adversarial Network. Just giving you an intro to a little bit of the terminology, but if you hear the word GAN, that's what people are talking about. And I'm not going to get into so much how these work in this, but just to overview the capabilities. Next, please. So as mentioned, for each one of these kind of types of neural network, there are a set of tasks that you can think about in planning that might be useful for. I think a very early and very useful task that's come out of some of these is counting pedestrians. So in New York City, there's actually a startup that is doing this with cell phones, and so you can use their app in the city itself. It doesn't have national coverage yet, but you can get pedestrian counts for most of New York City. And the accuracies of this are really pretty impressive. So, 97.5% accurate. And you can get some additional information beyond just the pedestrian counts. You can actually see how fast people are walking. And I guess there are fancier applications that can tell men from women and adults from children. But just having the ability to do pedestrian counts is something where we as planners have been data limited for years and years and years, right? The way to get pedestrian counts was always you had to send staff out with clickers, and nobody wanted to do a lot of that. So I think we're going to have a lot better pedestrian data coming soon, and that's a really good use of this technology. Next, please. The second level of detail that I mentioned is localization, and also known as bounding box localization for obvious reasons. I guess the thing to say here is that this is where billions of dollars of research from the self-driving car companies is all going in. So this is getting figured out with a vengeance, and it's quite possible now to get pretty high accuracies at this very simple level. You don't really know, what kind of car or what geometry of car or if it's going to hit you, etc. But even the basic level of observing what's going on urban streets, David's going to talk more about that. But this is already working pretty well and is likely to get up into the 99%, accuracy levels soon. So it's possible to do this now with just imagery, without radar or without LiDAR, and the things you'd expect to be problems are indeed really problems. So your intuition about what's easy and hard in perspective imagery is correct. It's correct for you, and it's mostly correct for computers. If you're dealing with just RGB imagery, occlusion and shadows and perspective distance all still matter. It's a little different if you've got LiDAR data that you can see in the dark, or infrared where you can see how stressed the trees are. But with basic imagery, what you see as a human is what the self-driving cars are able to grab. And so we as planners should be able to get much better inventory assets for fixed inventory as well as utilization data. Next, please. And the kind of third level of detail that I mentioned, semantic segmentation, is also being applied in the world of self-driving cars. So there's a lot of work going in at this level. This has applications both in the perspective view and in plan view. And so you can use it to count bicyclists or utility line poles or traffic signs. And that can be done a lot. The vertical ones of those can be done a lot better in perspective view than they can from an ortho photo. But the exact same technology can be applied to a perspective view image or to a map. That's very different for somebody, at least like me, trained in GIS, where it was very, very hard to get data from perspective imagery prior to this. But we're getting the point where perspective imagery is going to come back because you're going to be able to get lots of information from perspective imagery. Used to be that was really, really hard to deal with. You couldn't figure out the quantities or the sizes of things. But these camera systems know perspective, and so they can calculate sizes of things even if they're on a 2D image. Next, please. So a really good example of this, I should have put a better reference, I'm sorry. But there's a fun study, University of Chicago folks went down to the Galapagos and did an interesting job doing basic infrastructure mapping for all the small communities in the Galapagos using some commercially available current software and head-mounted cameras on bicycles. So you could go from classic technological leapfrogging, a place that didn't have any mapping data at all, get some people out on bikes taking perspective view imagery, and end up with a pretty nice automated assessment of urban infrastructure. So in the final version of this that we distribute, I'll try and put a better reference on this one. Sorry, I missed that one. Next, please. So as mentioned, this technology, when it's applied to orthophotos or satellite photos, basically gives you categorical maps. And I guess I'd say it's important at this point to realize kind of roughly how good it is. And I think these illustrations show that fairly well. You get blobby level structures, for instance. You get blobby level stuff in general, but you get pretty good counts. And so it's still not quite up to the quality of planometrics, which you can buy and they'll send them to India and spend lots of time digitizing. But this can now be done in an automated fashion with computers. And the nice thing is the computers never sleep. So you can apply this again and again to current imagery, recent imagery, and you'll get new construction, for instance. Don't need to wait for next year or next 5 years for other institutions to regenerate data. You'll be able to extract out reasonable land use plan cover from reasonable imagery. And I guess the last note on this one is I think it's important as planners that to note that you can have a little more agency about which classes are represented in your maps. With this technology, we don't need to have like a single national committee deciding what's in our land use land cover. So if you want to do urban outbuildings and you need an inventory of those, that's quite feasible. Basically, if you can see it well by eye from the air, machine learning will be able to pick that up. So there are a larger set of systems that are going to be extractable from this. The commercial applications so far are focusing on the common stuff, but the technology is really allowing you to go in and look for accessory buildings or look for retail versus commercial, distinctions that have always been important in urban areas, but have never been on most of the maps available to us are going to start to become available thanks to this. Next, please. And then lastly, the image synthesis part that I alluded to earlier, I think has real potential for planners. And so this notion is basically something planners have been trying to do for a long time. We never seem to get the resources that Hollywood does to illustrate our comp plan. So the thing that's different and important here is not so much what can be done, because Hollywood studios can do this today. It's kind of the level of expertise and money required. And so, this is a study, just for example, from a couple years ago with Photoshop, people photoshopping in trees that don't really exist and doing a study of human visual preferences relative to green infrastructure. Next, please. This is kind of the new technology applied to similar things. And so you can basically go from a map that you draw to an image. And that can be done for buildings in this kind of level of detail. Next, please. Or it can be done actually for entire landscapes. And so this is an application that was just demonstrated last week at SIGGRAPH, the Computer Graphics Conference in Los Angeles. And they literally sketched live the very, very simple map you see on the left. And the system is generating this kind of seamless imagery on the right that is, if not photorealistic, pretty darn close. And so from what we know already of perceptual experiments, that's going to be plenty close enough to do image simulations for urban planning applications, for instance. So expect a lot of this technology in the next couple of years to really come online for general purpose. But then as planners, I think we can use it proactively to illustrate how, for instance, a change in a forest plan, if you're at this scale, I guess, might look, or how an urban streetscaping project might look. So I think that's an area for us to push, basically, because the technology is coming together really quickly right there. And the stuff has gotten a lot of publicity for its bad uses, but I kind of want to emphasize the good use here. So So we can use it, people can use it to generate nasty fakes and try and fool people, but planners can also use it to do a positive vision of the future and show people what stuff might look like. And so I think that's going to be an important use. Next, please. So overall, just to look at the strengths, weaknesses, opportunities, and threats, this is extremely fast-moving technology. So an example of that's the diagrams on the right showing how much R&D money is going into it. It's gotten more application already than you might think. So the telecoms are using it. You know, the average use is in the private sector is 20 or 30% perhaps. So a lot of people are starting to use this stuff in various verticals. But as planners, then that kind of brings up two questions. So we need to kind of always, when we're assessing new technologies, think about it instrumentally, like what are the things we can use this for in planning, but also what are some of the social challenges that are going to be coming along with this technology that we also as planners need to deal with. Next, please. And so I would be remiss if I didn't talk, at least briefly, we can talk more in the discussion about the darker side of DNN. So I boil this down to 3 principal points. So first of all, privacy in machine learning is off by default. So it's possible to add it. Some of the major tech companies do, some don't, et cetera, but we lack policy and guidance on a lot of that stuff. And so that's obviously going to be a concern every time you're deploying any of this stuff. And you need to think about it because the technology is not mature, and the industry is not mature, I would say, in how that's handled. The second, maybe even more important thing that's specific to machine learning is that biased data replicates biases. And the study on the top, for instance, is a good example. So Amazon's Scrap's secret AI recruiting tool. So if you build a system by scanning all of the resumes that your company's ever received and calibrate that against who got hired and didn't get hired, guess what? You'll probably replicate exactly all the biases that your hiring practices ever had. So that's not the machine being vindictive. That's kind of a nasty reflection of ourselves, but it's a real issue when you're training on historic data. And so that's come up in a bunch of contexts already with machine learning. So the second headline indicates, AI programs exhibit racial and gender biases. And by the way, there's stuff with children as well. So every time that you have a very large training data set required, there's easy ways to get data and there's hard ways. And to get balanced training data is always and still hard. And so, that's kind of why I emphasize the need for large amounts of training data up front. And so add to that the need for large amounts of unbiased training data. That's a cost. That's a real cost. And I guess the really important thing to realize is that that's a hidden thing in the way most of these models work by default. So if you're evaluating the results, you're buying this technology, you need to be the educated consumer asking, hey, has this been tested for racial bias or bias against women? Like, what is the training sample that's used, and is it really a balanced training sample that reflects my community? And then I kind of mentioned the third issue, which is perhaps the most obvious one, but is image simulation going to be used to inspire people or to fool them? Basically, probably both, right? So the general public's going to have the ability to create really convincing fakes and not just images, but actually videos as well. So that's a red flashing alert socially. The planning implications of some of that we have yet to see, but I'm pretty sure that people fighting projects are going to fake images to show those projects in their worst light, for instance. The possibilities are pretty widespread. Next, please. So if you want a fun and artistic view, I didn't want to try and show a video live over the webinar because I was pretty sure it wasn't going to work, but down at SIGGRAPH in LA last week, I saw what I thought was a pretty brilliant artistic presentation on the limits of deep neural networks. And so this artist named Mimo Atkin basically trained neural networks in isolation on different sets of imagery. And so in this case, on the top line, he trained a neural network on 10,000 images just of fire. And that neural network has only ever seen fire. And then on the bottom, he did the same with 10,000 images of flowers. And what he does is then he points a video camera at some random clutter on his desk and asks the deep neural network to interpret that imagery. Basically, he's exposing the internals models of these deep neural networks. And the model that was trained on fire sees everything in the world as fire. And the model trained on flowers sees everything in the world as flowers. So it's a really good reminder that the current DNN technologies can't see very well or generate images outside of their training data. And that's back to that issue of kind of what training data goes into these systems, but it's artistically expressed here. So I recommend that video if you want to chase it down. Next, please. The reference is on the slide. So, just to summarize, training data needs to be really carefully considered in these systems, and there are definitely issues of unconscious bias or historical bias. And we are going to have a deluge of fake imagery and video. Hopefully, we'll be able to generate some useful versions of from the technology, but we're definitely going to have a lot of it. Next, please. But it's not all bad news. On the strengths and opportunities side, I think the technology is already demonstrating the ability to collect quantitative street level data, as well as data from conventional orthophotography kind of stuff. And that's going to let us have more granular classes than conventional land cover mapping, as I mentioned, and the ability to collect special purpose map data. And finally, that ability to visualize alternative futures without a Hollywood budget, I think could be a great opportunity. And I think that's all I have.
Michael's presentation really did a great job of discussing the history and background of computer vision. Mine kind of focuses more on what's possible for planning practice, and I think Mike also talked about what was possible as well. But I recognize that this is a very broad topic, and so this presentation might give you more specific on what tools and vendors might be out there that can help you with your projects. And so I think this is something that we've already discussed, so I'm not going to spend a lot of time on this slide, but thinking about what computer vision can do for urban planning boils down to it can measure anything that we can see. And a really promising aspect of this is that some of the qualitative aspects of urban life could potentially become more quantitative. And so the goal of this presentation is just to connect how computer vision can be connected to help planning practice and give you some of those examples. And as I prepared this presentation, one of the important pieces of planning literature that I used was William White's Social Life of Urban Spaces. And it provides a great example to me on how computer vision can fundamentally change how we approach planning practice. And for those, I guess a quick round of hands, how many of you are familiar with this work, this body of work? It was actually, a lot of it was done in New York. Okay, great. The body of this work was William White and a team of academics and interns used a lot of video review of urban spaces in New York City and also did a lot of time series observations with time-lapse photography. And they did a whole ton of interviews of people in these spaces to kind of ask them how they use these spaces, where they sit, how they use the space, socialize, or even walk through different types of urban spaces. And one of the questions that I've asked myself is how might a similar study be done today? You know, in the future, is the expectation that this technology will enable us to have automated counts by mode of who uses urban spaces, potentially provide information into behavior and what they're doing. Are they talking? Are they traveling with somebody? and even further, can it trace what paths people take and provide a sense of, you know, what types of aspects of a place are things we want to focus on at a more quantitative level. And while this mixes with issues of surveillance and privacy, this thought experiment really illustrates how this technology can change practice. It helps us see the things that we've done traditionally as a qualitative observation are now potentially quantitative or can be in the future. And some of this has already been discussed. For computer vision to be useful, you need imagery. Mike already discussed there's overhead and there's perspective imagery. One of the things that he hinted at is one of the projects I'm working on, but it's not really the focus of this presentation. Is one of them is synthetic imagery, and we kind of discussed how GANs can create synthetic imagery, but you can also think about it in terms of 3D models, for example, and renderings can create synthetic imagery that could potentially be used to help train better machine learning models. But I think these two main classes that we see in day-to-day life or as work as planners, overhead versus perspective, are the ones that we typically focus on the most. And so now I'm kind of going to go into the vendors and the examples of projects where we've used computer vision to kind of help move projects and planning conversations forward. And while not a comprehensive list, there are three broad classes of data that I think computer vision can really be helpful to help measure as part of projects and programs. And those three are right-of-way and assets, and by that I mean what's in the street, what street signs do we have out there, are there traffic lights and signals, behaviors, you know, how are people using spaces, examining some of the same types of observations that William White might have, and also the built environment. Where are the buildings, what are their sizes and massings, and where is the most intense uses. So the first one is right-of-way and assets. And planimetrics from imagery have always been possible, but I think now, as Mike alluded, it's going to become cheaper and more insightful. And there are two main types of asset inventories that come from two different types of imagery. Acopia Tech, for example, or Acopia.ai uses overhead imagery to extract vector data from high-resolution aerial imagery. And then there's another one, Mapillary, which does a lot of work to extract street signs, bicycle lanes, and other types of asset information based off of perspective view images that you can take on your smartphone. If any of you perhaps get bored during the presentation, you can actually go look on the App Store right now and download Mapillary onto your phones if you want to kind of experiment with this application for your own work. But it is a freely available application that will crowdsource imagery. And I guess the two examples I wanted to give here is for Acopia Tech, we found this type of computer vision derived right-of-way information to be incredibly helpful. One example was a active transportation plan in West Valley, Utah, where we were provided a roadbed width and a sidewalk inventory for a relatively low price compared to getting the same data manually. And you're seeing a screenshot of that on the left. And what it enabled us to do was know where the sidewalk gaps were at a very wide scale and at a price point where pretty relatively low budget active transportation plan, we were able to give them a data set they did not have in their region. And so it can be a very powerful tool to get this type of information on projects very quickly. It's important to think about what types of opportunities exist when we look at a technology that can get this type of asset information at this detail, at this scale. And as part of that, they threw in crosswalks, which you can see as those pink boxes in the image as well. And they're able to do more detailed extractions as well. So on the right, you can see more vector-based extractions of where the sidewalks are, where the driveways are. and even where the median and other types of lane features are. In the case of Mapillary, you can basically mount a phone to your car's dashboard, drive down the road as part of a typical type of field work, and they will take your images that you take about once every 1 to 3 seconds, and they will upload it and process it and extract out every street sign that you see and every type of asset that they can pick out of the image and map it for you. It's a great way to provide a very clear insight of what your site looks like as part of field work. So you can go out to the field, collect all this data, and then proceed to basically have an AI assistant extract out and geocode a lot of things that we might have had to do manually before. And I think one of the examples that comes to mind for me of how this data can be useful even at regional scales is the Alameda Multimodal Arterial Plan. This was a very large-scale plan that aimed to identify where the best multimodal improvements could be made across all of Alameda County's arterial network. For those who aren't familiar with Alameda County, it's right across the bay from San Francisco. It's where Oakland is and a lot of the East Bay and the San Francisco Bay Area. And it's a very large area. And as part of this project, we developed a very rich cross-sectional database manually over the course of months. This was a very laborious task, and it took a very long amount of time with the collaboration of multiple consultants to pull the database together. But the value that was added was pretty high. We could query where there were bike lanes and what width they were, how many lanes there were, and based on that, make recommendations and performance metrics across the entire network. But one of the creative things that we did is, because we had this database representation, we used a software program called City Engine to procedurally represent from the baseline conditions of the road network, but also the proposed improvements based on our edits to that cross-sectional database. And it enabled us to create these visualizations of complete streets at scale. And so it kind of illustrates how this type of asset information can be integrated from a regional scale to provide locally relevant recommendations to cities. On human behavior, again, this connects back to the social life of urban spaces, but it has very large implications also for how we approach systemic safety analysis, urban design, and transportation planning at large. I think the broad promise of the ability to take samples of human behaviors is it potentially opens up this opportunity to provide continuous information on metrics that relate to how our public spaces are being used. This could be how people interact in public squares. It could be near miss collisions at intersections, or other types of behavior that was hard to quantify before. An important implication of this is that we can potentially conduct A/B testing of the built environment. We can have cameras installed at a intersection, for example, in the case of Brisk Synergies, and install a curb extension and see what the changes in near-miss collisions are based on that. It can potentially help us identify what types of opportunities we can create for how we do potentially construction phasing as well. In the case of Numina has a hardware installation device that you install, and it will provide these traces of vehicles and pedestrians at different times of the day. And they do this using a technique called edge computing, which means they're computing all of this at the hardware device and then sending the traces to the city. So no one's identity is revealed from these images. And as part of the circular study in Brooklyn, one of the things that Numina was known for is they examined how the placement of scaffolding changed pedestrian behavior before and after the scaffolding was put up. So you can see here the ratio of pedestrians that started walking into the road increased about 53% after scaffolding was put up. And it's a type of intervention that we've seen in the urban environment all the time. It's one that people usually find annoying, but it's something that was potentially not something we would try to even quantify because it wasn't seen as a high priority. But maybe these questions of construction phasing have pretty deep implications for safety. And I think the planning implications of this is pretty clear. It kind of takes a lot of the aspects of our work that are more qualitative. It can potentially make them more quantitative. It enables before and after looks of how behavior changes as a result of interventions. So it enables us to be more accountable to the populations that we serve and in the urban areas we're trying to improve. But it also opens up a lot of privacy concerns. I think as Mike mentioned, privacy is not built in by default. And there is kind of this concern with a lot of these machine learning technologies. Are we potentially making a panopticon of sorts where people feel they're being watched at every moment? But I think, again, there's still a huge amount of opportunity, though. I think we need, as planners, we need to address these privacy concerns head on and think about what types of solutions that we can do. I think a very popular example from the New York Times was Alex Bell's Our Camera project, where he set up and trained his own model, a box model, looking at how often and when people are blocking bus stops and bike lanes. And this was something that someone did on their own. Just as Mike said, anybody might be able to make these technologies potentially to make fakes and fool the public. It's also possible that we could find solutions from our own communities and find bottom-up ways of solving problems based on how this technology is deployed and whether it gets easier to use. One of the last things I wanted to go over is built environment traits. And for me, one of the big things that comes to mind is land cover classification and 3D models derived from imagery. And this isn't entirely new. I think a good example of this is photogrammetry. You take a picture from multiple perspectives and you're able to reconstruct a 3D representation of what you're seeing. I think with AI, you're seeing a lot of these types of processes get faster, more efficient, and provide higher resolution and higher quality product. And I think, 3D models again and again in planning discussions as either potentially contributing or taking away from the process. But they provide this opportunity to engage the public on what changes are actually occurring in urban environments, to visualize them, and to potentially gamify them. And the two vendors that came to mind for this, one is Ecopia, is one of the previous ones I mentioned, alongside providing sidewalk and street inventories. They've shown and demonstrated they're able to do some 3D footprint extraction. And another is a more recent vendor is GeoPipe, where they're mostly focused on providing highly detailed building and streets that are used in a variety of video gaming types of platforms such as Unreal and Unity, and within the AEC industry. And I think when we, at a more regional scale, these technologies enable us to monitor land use change at a pace and scale that just previously wasn't possible. We could potentially create models that help us in identifying robust ecological inventories, getting detailed monitoring of farm and wetland conversion. But even with these models, we can start looking at more detailed problems such as shadow impacts of new construction and how they change how people interact with a certain space. The big planning implication here is our regions becoming affordable. A lot of this data that computer vision can help us collect used to be stuff that we would collect locally on our own and manually, just like in the case of the Alameda Arterial Plan. And is it now coming to a point where a regional understanding of what is on the ground is something that can be afforded? And if that is, does that mean that every city in the world could have some type of 3D representation that could be used for planning applications and analysis. But also, I think it brings up this question of what data do we want? As Mike illustrated, the flexibility of these algorithms is that they're able to take samples of anything and potentially provide labels of those things that are relevant to solving the problems that planners have. And I think a big thing that planners should probably start to think about more and more is, what type of data specifications do we want to see come out of these processes? These aren't very well-defined things. These aren't, the people are making products and features without understanding a lot of the problems that we're trying to solve. And maybe it would be on us to be proactive about what types of things that we want to look at. And one example that is one I'm working on a little bit with a few folks is the shared right-of-way specification is one thing that comes to mind. As I mentioned with the Alameda Arterial Plan, it's a very large headache to collect all of that right-of-way information. And maybe we should start thinking about a right-of-way specification that can start collecting the types of information that we want for a new enhanced center line. And if we put out the requests now, it's something that we can start to build on in the future. Some of this, I think, Mike addressed head on, so I'm only going to spend a little bit of time on it. Computer vision definitely has its limitations, and I think one of the big ones is the quadrants of knowledge still apply. You know, the previous labels that you collect are the ones that will be what these processes provide to you once you go out to collect data. So I think a good example that comes to mind to me is field work. When we go out to do field work, we don't always know what we're looking for. And if these algorithms are only looking for specific things and we only go out to the field afterwards and we determine, oh, you're right, there's this one aspect that we crucially missed. Now we have to go back and collect all that data. I think this is something that we just want to keep in the back of our heads when we think about these technologies is, I don't think this replaces fieldwork, and I don't think it replaces critical thinking. It just could help make some aspects of our work easier. And the second thing is, I don't think a lot of the existing training data sets that exist have an urban planning focus. I think some of them are getting better. I think Mapillary is actually a great example of this as a data set provider that helps illustrate what's possible and what can have a very urban, or what type of training data sets can have an urban planning focus. But a lot of the industry is currently focused on autonomous vehicles, navigating streets, and those types of systems. And so sometimes you get things where certain labels don't exist. So for example, there aren't many training data sets that know what a bike lane is or label one. And sometimes when they do, in the case of the Mapillary Vistas data set, and I've been told they fixed this, but I've looked around some data sets and I found the things that have been labeled as bike lanes, for example, were actually bus lanes. And you know, those are the types of things I think planners need to articulate and voice whenever there is an issue in these data sets. And I'm going to conclude basically around here is one of the big opportunities with computer vision based technologies is it enables us to scale up our understanding of the existing condition in a way that wasn't possible before. You know, maybe our MPOs or council of governments are able to purchase regional scale data so that a lot of these cities and urban areas that we work with that have less capacity can start doing a lot of work with detailed road and sidewalk inventories that couldn't do it before. One of the great things I would like to see come from this is being able to take this regional scale data and make it locally relevant in a way that we couldn't see before. I think one example that comes to mind for me is Gothenburg, Sweden, and how they developed a 3D model of their city was one where they not only did a lot of work to get data on the existing condition, but they developed a lot of rule-based creations that could be iterated on very quickly. They could change a parameter here and a building would become instead of 3 stories, 4 stories. They could explore different types of setbacks and urban form. And they could iterate on those ideas with city architects and stakeholders in a very quick way. They had a very dynamic representation of their city that they could edit and assess the impacts from. So this kind of brings me to where are we heading? And even in the last planning magazine, I think one of the letters mentioned there talked about the concept of VUCA from the 1980s, the concept that we're heading into a future that's volatile, uncertain, complex, and ambiguous. And I think a lot of that is from the fact that a lot of the future feels very dynamic and very fast-paced, and especially in our cities. We're increasingly looking at interconnected social and economic systems, but also there's a lot of uncertainty. And whether you're thinking about things like climate change or how trade policy influences urban policy or vice versa, there's a lot of questions that remain open in terms of how planners are going to assess and deal with a lot of the interacting forces that are transforming our cities and frankly our planet. So I think a good steps forward are to think about how we build data-informed and adaptive plans that I think are going to be needed to manage new risks. We need to think about how multiple domains are relevant to urban problems. You know, the science of cities is more than just urban planning. It's everything from urban ecology to urban sociology and a vast degree of other disciplines. And also, I don't think we can build our cities optimizing on one variable anymore. I think we're going to have to be able to think about multiple goals and how we balance them, and also what types of metrics we're going to hold ourselves accountable. I'm going to conclude on this is that computer vision really helps us break the mold of keeping these static representations of the world, whether it's in PDFs or something else. You know, we need to break ourselves from paradigms that require us to think as one existing condition. You know, this is what this plan says the world looks like today. And I don't think that's realistic. I think to plan for an uncertain future, we need technologies that help us plan adaptively and think about change as part of the process. And these technologies can help us reduce the time it takes to develop that understanding. So that's my presentation now, and I'm going to pass it back to Marshall to kind of give a sense of what potential next steps are.
Thanks, David. So yeah, what are some next steps for everybody here and on the phone as well? You know, how many people have a GitHub account and understand how to really use Git? You know, there's so much great content that you can follow in repositories in GitHub and a variety of other Git resources out on the web. You're able to use open source versions of Git internally for your own work and to collaborate with your technology department and get to buddy up with your CTO and your system application supervisors. It really allows you to leap forward in understanding a lot of contemporary work out there and leverage a lot of the open source technology that's being developed and contribute to it. You know, folks, I'm sure a lot of you probably use Reddit to stay up on a lot of latest tech developments, whether good stuff, bad stuff, and everything in between. Stack Overflow is another really outstanding resource for finding solutions to many of the questions that you might have. You know, getting into the data, it's kind of what David was talking about in standardized data for the shared right-of-way specification. And one of my favorite ones to always talk about is actually the BLDS. It's the Building and Land Development Specification, which is really focused around permit data, from planning permits all the way to occupancy permits. And when you're dealing in a regional area, it's very powerful to be able to translate individual permit databases from different jurisdictions into one common schema. and how important that is to us conducting quality work in an efficient process is invaluable. A big question to ask both David and Mike in a little bit is, how do you QA data in your project, especially if you're using machine learned data and not being super proficient with the technology and understanding it. So we'll get to that in the QA. Something else I like to talk about is when you're actually digging in on your data and doing your analysis, is it appropriate to be just using it in Excel, or should you be leveraging SQL and SQL-based databases to help you crunch through queries and do your analysis? And additional contemporary ways of doing this are using notebooks, whether you use Python or R. And are those going to be deliverables moving forward for you as a public sector employee, or for you as a consultant to a jurisdiction? Another thing that I think is really important is for project managers to really work with your contracting department to make sure that there is equity in RFPs and the opportunity to have startups and young firms be in the same ground level and same standing as established firms that are more fluent and have larger experiences and deeper pockets to put in a good bid and have an opportunity to win a project that might be more innovative and applicable to what you need in a lot of the dynamic changes we're having in our cities. So really working with your contracting department and your legal department to help them understand, to remove some of the barriers on access to submitting contracts. It's very important. So with that said, I think we're going to move into Q&A, and I just wanted to open up some Q&A and open this to both David and Mike. I'm not going to ask all these questions. There's just some out here as examples, but the one I was really interested to hear what they had to say is, how can you be prepared to quality control AI-derived data?
Sure. So the good news there, I guess, is that there are kind of built-in methods for testing machine learning data. And so the models are built by testing a metric of the model's quality. So certainly you can ask for those metrics. So for example, I just bought some land cover data, and I required that we see the accuracy statistics at the class level for that data. Oh, I guess I should start my video, sorry. So you can ask for the QA data on any AI-derived project data, and should. So that's the good news side. Then the bad news I already shared with you a little bit, that's internal QA data. And so it's based on the same training set that was used to build the model. And therefore, you should often think about testing the model outside of that data set provided by a vendor. And so that's the acid test. And I think that's kind of the second thing that's important about that quality control. So you have to spot check things, but generally, I guess my answer is that we use a kind of stratified sample to spot check things. If it looks to be in order, then we test it a little bit, but we're limited in our ability to test extensively. So where we can contractually, we try to make sure the vendors provide accessibility to their quality control data. And in the machine learning case, you can't be shy to ask, because that's kind of one of the main things that these systems provide.
I think from that was actually one of the first things we did last year. Was quality control was a big thing that came up, where we wanted to see what can this data be used for, but also how often is it right versus wrong. You know, from Acopia, when working on the West Valley, Utah project, it was pretty easy to do some pretty quick checks on the sidewalk data, because what we really wanted to know about was gaps. So we knew we had a centerline database, for example, and we could say which of these streets don't have sidewalks next to them, and we could go verify what that looked like and if that was correct. In the case of Mapillary, you can get a lot of great asset information and where it's located from their image detections, but even their image detections aren't perfect, and sometimes it's dependent on the imagery that you give them. If you give them GPS ping traced imagery, for example, that bounces all over the place, the detections can be in a weird location. But beyond that, you know, sometimes the Orkin man sign gets confused for a stop sign because it's a red hexagon with white text in the middle of it. So, you know, those are the types of things you have to be aware of. But they're things that you can check. You know, stop signs don't happen in the middle of intersections, or sorry, in the middle of streets usually. That's probably a usual giveaway of the types of rules that we can think about that could be used to sanity check a lot of the things that we look at.
Thanks, David. Thanks, Mike. Olivia, do you want to open up the questions to the floor and have folks maybe come up to the mic or bring the mic to them, however?
How can machine learning be used with big data sets, say data sets of terabytes or petabytes in size for planning purposes?
Mike, do you want to take that one?
Start on that one. So I guess the first thing I would say is that I probably should have mentioned this, but machine learning is typically dependent on graphic processing units or GPUs. So the video cards that all the video gamers have graced us with at $40 a pop are really actually very powerful computing machines. And so the pipelines or the systems that support machine learning are often based on GPU, and therefore are often very efficient. But from a planning perspective, I guess I'd say that the thing you have to think about is how you can divide up the work. And if you can divide it up into units that are independent, then with current cloud technology, you can distribute those across many, many machines. And so I just finished a project where I did a map of every eucalyptus tree in Portugal. And there are a lot of eucalyptus trees in Portugal, 90,000 square kilometers, more or less. And at the peak of that, I'm running a five-person firm. We had 1,000 CPUs running in parallel, working on that project. And that was perfectly fine because we could do it tile by tile in parallel. So the general answer is use GPU where you can first, because if you keep stuff in one machine, it'll be faster. But if you must, go across multiple CPUs, and if you don't own 1,000 of them, rent them from your favorite cloud provider and use them for 10 hours and then throw them away. So that's kind of, a little quick tour of the technologies, but basically those are the options. Like, get it to run on one big server. If it can't run on that, get it on GPU. If it can't run on that, you got to figure out how to break up the problem across many machines. But the machine learning workflows are built for that kind of data volume. So the good news is that the technology is really designed for that.
And I think also it's still a question of how much planners might have to worry about the hardware versus the software and how we deploy these models. Fair and Peers has gotten a lot of value out of using vendors that are very versed in being able to synthesize and analyze this type of very big imagery data, for example. And maybe that's just the start, is just trying to see how you can use this as part of your work today. I mean, I think most people here could go back to their offices and use some of the things that we talked about, whether it's the Mapillary app or some other type of technology that uses these types of methods to extract data from.
Yeah. I forgot I'd be remiss if I didn't put in a little plug for one of my clients. So I work a lot with a company called OmniSci, used to be called MapD, and they make a database that's a SQL database, which runs on GPUs. It'll fall back to CPUs, but it runs on graphics cards. And there's an open source version of that. So if you like, check it out. There's also a very expensive commercial version. The difference between the two is the open source version runs on any one computer with as many GPU cards as you can pack into it, and the expensive version runs across a whole data center. But there's a quite capable version on a modern big server that you can rent by the hour from Amazon or other cloud providers. You can do massive amount of data work. And so I kind of recommend that as a starting point because it uses SQL, and most of you probably are familiar one way or another with SQL. So it's kind of got a standard interface, just like the database behind your average GIS, but it's got more performance oomph. So if you find yourself needing to run through, I would say basically if anything runs on your local computer, fine, keep using your local computer. But when you get into millions of records to billions of records, then traditional, processes start to break down. And that's, in my case, I end up using OmniSci because I like the combination of an easy user interface. It's got a graphical interface and it's got a SQL interface. I don't have to learn anything particularly profoundly new to use it, but it can use hardware better than kind of conventional GIS or CAD programs.
Any other questions?
All right. Thank you guys for the presentation. I'm an engineer at Numina, one of the startups you guys mentioned earlier. And like at that deployment in DBP, we often have the chance to work with planners, but we don't have any planners on our team. So I was wondering if you guys had any suggestions for those of us in the tech community for next steps for how we might be able to better understand the data and metrics that are most valuable to planners.
Wow.
As an academic, I guess I would say that I think planning students are the world's cheapest resource, and more about planning. Having an internship program that brings in young planners cannot be beat for price performance. You will get more than an earful of planning speak, and you can kind of touch base with the next generation of planners that way. So we have an internship program. I've started one at one of my clients. So I do practice what I preach there. So that's to me the simplest way to get started. And then you're already a member of APA, so there's a lot of other APA things, but other people can talk about that.
Yeah. I think also you'll find that whether it's planning firms or organizations, getting into the spaces like you're doing right now where planners are and being able to network at those events has been very critical, I know, for me in terms of what I've learned about people in industry. I know I've met a lot of people either at APA or at the Esri UC, the Esri User Conference, where a lot of these vendors were presenting. And I think I'd advise, making sure that you're able to make contact and just start conversations. I think it's the easiest thing to do.
Yeah, joining professional organizations and networking in APA, you can join, something that'd be really applicable with the transportation planning division and be able to network with the transportation planners and how, where everybody's nice and they're gonna help you succeed.
Yeah, and I guess we would be remiss if we didn't do a shameless plug for APA Magazine. I'm kidding, but I really mean that. A lot of the professional readings, the articles that come out of APA Planning Magazine are really good at keeping current on the types of conversations that planners are having, and what types of dialogues and problems we're trying to solve. question. Thank you for asking it.
All right, we got another one.
Okay. Hey, y'all. So from what I've seen in computer vision technology within the planning sphere, and a lot of what you're presenting on tonight is adding way more power to our ability to do broadly descriptive statistics. So, you know, we can look at an image and now say a lot more about what's happening, but I'm interested if you all have examples of machine learning, computer vision for more inferential statistics and getting more at causality and why these things are happening. You know, one of the examples with like the Numina example that you gave with the scaffolding and people moving to the road, it's like, well, yeah, we can see like, we can pretty reasonably assume this scaffolding is causing people
Sure.
to walk in the road. But like, what are some of the things that we can't see and that aren't obvious in the causal patterns that this technology allows us to do now?
Sure. I think a very important thing to think about is there are degrees of complexity that when we look at building even like linear regression models for, and I'm thinking the case of transportation more recently, direct ridership modeling. You know, as computers have gotten better, getting some of the more complex and theoretically consistent metrics has also gotten easier. And I think the descriptive statistics can inform the inferential and get to causality. It gives us more things. If we're able to describe, for example, where different types of assets are, where stop signs are, where signals are, believe it or not, that's data that's actually very, very hard to collect systematically for things like a systemic safety plan, where you only have, you know, a few $1,000s for data collection. So it really is, I think, part of that process of being able to get variables that you can test against and get variables that you can use to control for different aspects of the built environment and how it fits into, getting into a causal picture. I think it's going to lower the cost of entry alongside other open data sets like OpenStreetMap, for example. I think there's a lot of value in seeing how these derivatives can, for example, inform a lot of different types of models that we just couldn't even look at before. Mike probably has some really great thoughts on that.
Well, I would say a couple things. I mean, one is that it's a great question. The gold standard usually for separating out causality from correlation usually uses either time series or experiments.
Mm-hmm.
Or thought of another way, natural experiments versus designed ones. Inside big data, there are a lot of opportunities for natural experiments. So if you have every intersection in the city labeled as to, you know, its type of crosswalk, you can conduct a study to say, hey, did the crosswalk design materially affect safety given all of these other corollaries? So it doesn't change the kind of science that you can do using kind of a conventional experimental design. But what it does do is it gives you a lot more access to time series data.
Right.
It used to be nearly impossible to do before and afters, was expensive, and certainly to do long term was really expensive. And so the fact that you can collect, back to my example, you know, safety data, not just the week after you did the intervention, but a year later, where social effects start to an adaptation, human adaptation, start to come back into play. I think it was probably the single most important part. In my own work, I didn't show, but I think a lot of impervious cover detection that I've been working on is getting really well integrated now that there's time series data. And so I've got satellite imagery at 10 meters that shows soil moisture, and it shows impervious cover. And you can pretty much see how storms hit large urban big box parking lots and where the water runs off into the landscape. And so you're able to start to follow natural processes. Now we've had those snapshots for a long time, but having daily or weekly remote sensing data starts to let us see processes that were very difficult to trace before. And so
Yeah.
in that case, there are things we knew scientifically a long time ago, but getting local specificity, not just that it's runoff, but here's how your runoff is working in this neighborhood, I think is a big added value. So there it's a little bit granularity and a little bit of time series.
Yeah.
But I would say that all of this stuff is leading to better models and modeling, for sure. Not just descriptive statistics, but actually coming up with better models.
Right.
The really hard thing in that is that the default answer out of machine learning is you kind of have data in, and then you have this conclusion, and the mechanism is really difficult to determine. So I don't want to go too deep into that, but there are some definite issues with machine learning methodologies in terms of explainable AI. And in fact, there's a whole movement called explainable AI for exactly that reason. So the tools can be quite powerful at discovering correlations in the input data set. And there's a kind of movement about in machine learning to try and force people to be explicit about what the model's actually learning and how it's telling. So I have to give one quick anecdote. You just reminded me. So I took a course from Google's machine learning team last week down in LA, and one of the lead instructors took a photo of his dog and put it into one of these machine learning models. And his dog was a golden retriever. And he had a nice picture of the golden retriever with one of its ears up and one of its ears down. And the machine learning model said that his dog was an Australian dingo. And it's like, that's not right. The model's supposed to know what golden retrievers are. It had hundreds of pictures of golden retrievers. Why did it think my dog is a dingo? And since he's a Google guy, he was able to actually dig into the machine learning model and figure it out. And he figured it out by looking, kind of back to the first slide I showed, at the levels inside the model. And he found that the dog model was based on ears. And it was differentiating the dog breeds based on ears. And all of the photos of golden retrievers in the system had the ears down. And the fact that his golden retriever had its ears pointing up was what was causing the model to fail. So that's a real world story on a silly example, but I think the challenge remaining for machine learning models relative to that is to be able to give good explanations of why they came to a conclusion. And we won't be able to use them routinely as planners for important inferences until we do that, and we shouldn't.
And
until they do that.
And I think there's a good book I recommend by Jeffrey West called Scale. Very interesting book talking about adaptive complex systems, including cities. But one of the things that he talks about near the end of his book is how, machine learning, one of the things about big data and machine learning is when we think about this type of technology and scale and of data, it shouldn't replace the theoretical basis for which we build our understanding. I don't think we want to fall into the box of thinking correlation is all that matters. And I think the dingo story, Mike, actually hits right on that. I think that's exactly what we need to start thinking about is, this might help us get the inputs that we need to build our understanding of the world around us. I know, anytime I do a safety analysis, I don't know where the stop signs are versus where the signalized intersections are. It's embarrassing, but a lot of cities just don't have that information in a context where it's easily able to be deployed. And I mean, even just getting at these very basic questions of where things are, just provides an incredible amount of insight and a great way to build a theoretical foundation for why things occur the way they might be occurring.
So I want to just quickly talk about a project that NASA's coordinating. It's called OMG, or Oceans Melting Greenland. And the reason I want to bring it up is because, via remote sensing, traditional remote sensing satellite imagery, you can see how temperatures are changing and ice sheets are diminishing. But what their approach is taking on a variety of sensors from all different places and locations. And my point is that you need a variety of data relying on one resource may not be completely applicable to your problem. And then being able to create a very systemic way of integrating a multi-criteria decision analysis process and matrix. And that can enable these data resources that you previously didn't have access to help solve these problems or provide alternative answers to the questions you're asking.
What are some of the public policy concerns for using machine learning to do predictive analytics? Say if you have a bunch of crime data and you extract that crime data to predict a crime, of course you want to have an officer where there's a hotspot of crime, but
Right.
this could go to the point where someone shows up at your door because the machine learning model determined that there's going to be a crime committed in your house, even though it's just you.
Right. That's a great question. I'd like to take this first. And if we go back to the March issue of planning, Sidewalk Labs identified 4 key components of digital governance, and it makes a lot of sense. And the first one's civic data trust. The second's published standards. The third is responsible data impact assessment. And the fourth is responsible data use guidelines. And additionally, as a kind of one of my first slides talking about open data policies, it's really important to have a vetted out data stewardship and open data committee that will assist the city or the jurisdiction or whoever it may be in understanding how these data resources should be used, stored, protected, secured, what kind of analysis they should be leveraged for, and to carry on with that. And another component that I think there's going to be a really great book coming out called Uneven Innovation, the Work of Smart Cities. And I think that's going to get into some of the security implications you're alluding to in your question. So Mike, David, I don't know if you have anything to add.
Yeah, I think we already discussed the scrutability problem, I think, to some extent. I think Mike's examples are perfect for that. So I'm not really going to discuss much more about that. But I think being understanding of the transparency of the assumptions that are being made is really important. And there are some types of simpler models that can provide sometimes better accuracy, and if not better accuracy, a better understanding of how different variables are interacting. I think one example that comes to mind is we recently wrapped up a direct ridership model for Caltrain and BART, for example, and we explored potentially variable selection with machine learning methods such as random forest modeling, but we ultimately went back to linear modeling so that we understood what we were doing, because I think the fact that these models, you can't inspect them, but they, as you get to increasing levels of model complexity, the level at which they can describe what's happening or be consistent with a theoretical understanding of the problem, sometimes starts to shift or change and not really be understandable. Mike, do you have anything to add there?
Well, I liked Marshall's overview. I think was a great set of places. I think the topics not covered. Yeah, I hesitated to get into it because it's technology on top of technology. But this notion of taking very complex machine learning tools, using them to select variables or propose essentially a hypothesis, and then testing that, has been used to good success by multiple parties. And
Right.
I just went to an ag tech startup talk the other week. They had 30 different variables explaining farm productivity. Their model did all kinds of fancy bells and whistles, ended up 3 things were really important. They made a simple linear model of those 3 things that was completely inspectable and understandable, and they had very high confidence in, and that's what they used with the farmers to execute on the project. So it is quite possible to deploy machine learning as a data synthesis and big data grinding machine, and then get some understanding out of that, which you then use conventional techniques on. And I think that's a great technique and a great use. I guess the thing about data policy that I'm perhaps the most nervous about, I think people are very well aware of the privacy concerns. I think the issue of the sample bias within training samples is really hard to get into public policy, at least so far. And I'm not quite sure the right mechanisms, but we know some of the biases to look for. And so there's a great MIT group on this topic. I can't remember their name offhand, but one of the MIT planning school groups is addressing this issue of bias in machine learning models head on. So I'd recommend looking them up as a resource. But in general, look for bias because you're going to find it. And so look for biases that have historically been a problem, racial biases, gender biases, etc. You probably won't be surprised because where these tools are trained on biased data sets, they will have those flaws. And so you kind of need to, as a consumer, to ask about that and look at that, particularly if they're being used in any kind of public policy context. But I would argue even as an enterprise, if your resume scanning system is systematically biased, you're going to be in pretty big trouble. So either ask for a simple version of outputs or make a simple version of outputs that is explainable and defensible, or be really circumspect about the data that's coming in and look out for policies that require that inspectability of the data sets used to train the models. Because remember, people can be completely transparent about the model they use to train, the streetlight data. But if they don't tell you about the data that they used, you can't really tell what's going on. And so that's a new thing that's relative to the structure of these models, that you can't understand them just from looking at the model structure. The model structure is kind of meaningless. It's a bunch of weights. It's really quite difficult right now to interpret. So you have to put more attention on the model inputs and more attention on the model outputs for the moment. That's going to be the strategy for now. Hopefully the technology will improve and become more inspectable by default. But for now, I would say pay double the amount of attention you're used to on the input data and look for racial bias, look for gender bias, look for age bias, whatever it is. But be really careful that you're not replicating the problems of the past by through this implicit bias problem in the models. So that's the part. The rest is all the good practice you already know.
Yeah, that's good.
Oh, hey, can everybody give a round of applause to Olivia for helping us put this on?
Yeah.
Thanks, Olivia.
I think the speakers deserve a round of applause, but I appreciate that.
Thank you, everyone. If you can reach out to any of us offline, and the conversation doesn't have to stop here by any means. And if any of the stuff that we talked about interests you, we're more than welcome to engage you further if you have other questions.